Here is a combined summary of the 4 pages. Mobile Edge Intelligence, MEI, is poised to revolutionize the deployment of large language models, LLMs, by bridging the gap between cloud-based and on-device AI. However, deploying LLMs on edge devices is challenging due to limited computing, storage, and memory resources. This survey provides a comprehensive overview of MEI for LLMs, covering edge LLM caching and delivery, edge LLM training, and edge LLM inference. The authors highlight the potential of MEI to provide a more powerful computing environment than edge devices but less powerful than cloud centers, enhancing resource efficiency, privacy, and latency. They identify key applications that demonstrate the need for deploying LLMs at the network edge, including smart health, autonomous driving, and augmented reality. The survey delves into the state-of-the-art approaches to edge LLM training, inference, caching, and delivery, emphasizing the importance of enhancing storage, computing, and communication efficiency. It introduces the concept of LLMs, including transformers and multimodal LLMs, and discusses the role of mobile edge intelligence in enhancing LLM deployment efficiency. The authors present a detailed survey of related work, summarizing various techniques for efficient LLM deployment, including model-centric methods, data-centric approaches, and framework-centric strategies. They also outline the importance of resource-efficient LLM techniques, including efficient inference, fine-tuning, caching, and delivery, and provide an in-depth analysis of edge training and inference for LLMs, covering centralized, federated, and hierarchical collaborative learning, as well as centralized, split, and collaborative inference. Future research opportunities include green edge LLMs and secure edge LLMs, emphasizing the need for continued innovation in enhancing the efficiency and security of edge LLM deployment to support various applications in mobile edge intelligence. Transformers have revolutionized natural language processing by introducing multi-head attention, facilitating parallelization and scalability, leading to the development of large language models that have demonstrated exceptional performance across various NLP tasks. These models can be classified into encoder-only, encoder-decoder, and decoder-only models, each with unique characteristics. Multimodal LLMs have emerged as a paradigm, amalgamating various modalities into a unified framework, empowering diverse and complex multimodal tasks. The primary challenge lies in achieving high-performance collaborative training and inference, with research focusing on refining modality alignment via multimodal pre-training and multimodal instruction tuning. The rapid development of LLMs has a profound impact on applications, particularly in generative AI and interactive AI. LLMs facilitate complex interactive dialogues and are regarded as the cornerstone of interactive AI. To enable AI agents to generate more accurate and up-to-date responses, retrieval augmented generation can be integrated into LLMs. Industrial progress for LLMs has been significant, driven by advancements in deep learning algorithms, increased computing capabilities, and the availability of large-scale datasets. However, deploying LLMs on edge devices poses significant challenges, including excessive computing overhead, huge storage, memory demands, and high energy costs. To mitigate these challenges, resource-efficient techniques such as LLM compression, quantization, pruning, and knowledge distillation can be employed. These techniques serve as the foundation for MEI for LLM, a distributed computing paradigm that integrates network-based AI algorithms into 5G networks, ensuring high-speed and stable data links between edge servers and edge devices. This paradigm offers numerous advantages, including latency reduction, improved bandwidth utilization, data privacy preservation, and enhanced resilience to network failures, with substantial implications across various domains. This research paper discusses the development of resource-efficient techniques for large language models, LLMs, to enhance their deployment on edge devices. The authors present a comprehensive summary of related works in Table 2, covering LLM compression, pruning, knowledge distillation, and fast decoding methods. They focus on the challenges of deploying LLMs on edge devices due to their large size and high computational requirements. Various techniques are proposed, such as LLM compression, pruning, and knowledge distillation, to address these issues. Fast decoding methods, including speculative decoding, early exit, and parallel decoding, aim to save computing resources and facilitate on-device inference. The authors highlight the limitations, assumptions, and future work in the field, emphasizing the need for further research to overcome the challenges of deploying LLMs on edge devices efficiently. The paper discusses the application of large language models, LLMs, in various scenarios, focusing on latency requirements, bandwidth costs, and privacy requirements. In mobile health, LLMs can deliver personalized health and wellness features, medical question answering, and diagnosis. For autonomous driving, humanoid robots, and virtual assistants, LLMs enable tasks such as ultra-low latency processing, high bandwidth data transmission, and sensitive data handling. The paper highlights the need for deploying LLMs at the network edge to meet these requirements, citing examples like Google's MED-PaLM2 and Tesla's Optimus. It emphasizes the significance of low latency, high bandwidth, and data privacy in these applications. The deployment of LLMs at the mobile edge is crucial for applications requiring real-time responses, localized data processing, and preserving data ownership. In virtual assistants, LLMs must respond accurately within a latency of 200 milliseconds to ensure a seamless user experience. Moreover, decentralizing data processing at the edge can reduce bandwidth consumption costs. Additionally, processing data on edge devices maintains privacy and protects data ownership. In autonomous driving, LLMs can provide in-car and autonomous driving services, handling complex and rare driving scenarios. However, autonomous driving relies on in-car and edge computing to support real-time requirements and preserve privacy. The latency requirement for autonomous driving is even stricter, with a 10 milliseconds E2E latency requirement. To address these challenges, the MEI4 LLM framework is proposed, which consists of 4 basic components: AI-native architecture, parameter sharing LLM caching and delivery, distributed LLM training, fine-tuning, and distributed LLM inference. The AI-native architecture features network virtualization, model splitting for training and inference, and information-centric networking for seamless model, feature, and data transmission. The parameter-sharing LLM caching and delivery component enables efficient edge LLM caching and low-latency LLM delivery by reducing caching and delivery costs of duplicate LLM parameter blocks. The distributed LLM training, fine-tuning component fine-tunes LLMs to adapt to local environments, preserving user privacy and data ownership. Federated learning, split learning, and split federated learning are promising distributed learning techniques to support large-scale model training. The MEI4 LLM architecture also features a central controller that orchestrates network-wide computing resources and data transmissions, with the decoupled control and data plane. By collecting global network knowledge, the controller partitions and coordinates model training, inference, and delivery across distributed edge computing systems. The research paper discusses the implementation of large language models, LLMs, at the network edge, focusing on caching and delivery strategies. It highlights the importance of exploiting parameter shareability in LLMs to enhance storage and communication efficiency. The authors propose the TRIM caching framework, which caches shared parameter blocks of LLMs only once on an edge server, improving storage efficiency. They also discuss edge caching for RAG, where popular external knowledge sources are cached at the network edge to enable LLMs to retrieve relevant data quickly. The paper emphasizes the need for efficient caching and replacement strategies, particularly in scenarios with high user mobility. It concludes by highlighting the significance of distributed algorithms for making replacement decisions without knowing full information of other edge nodes. The paper also discusses the challenges of delivering large language models in edge networks, particularly in scenarios where the requested LLM is not cached on the associated edge server. It proposes novel techniques to reduce the latency and costs of model delivery, focusing on parameter sharing backhaul and wireless model downloading. Efficient edge learning for large language models, LLMs, is a crucial area of research, as centralized approaches face significant computing burden and communication overhead. To address these challenges, the paper proposes various solutions, including scaling up LLM training using parallel computing strategies such as data, pipeline, and tensor parallelism, and GPU memory optimization techniques like zero. Federated edge learning is explored, where edge devices upload only the LoRa parameters to the edge server, reducing communication overhead. Split learning is also discussed, which minimizes communication overhead by sending informative smashed data to the server. Hierarchical collaborative learning, including cloud-end, cloud-edge, and cloud-edge-end collaboration, is highlighted as an important area of research. In distributed computing, resource management is critical for scaling up LLM training, particularly in edge networks with heterogeneous computing and communication capabilities. Model splitting and placement techniques are discussed to optimize resource allocation and minimize communication overhead. Importance-aware token uploading is emphasized, allocating more radio resources to high-importance training data samples to improve convergence rate and model accuracy. Federated edge learning is proposed as an alternative to centralized edge learning, addressing privacy concerns. However, it faces challenges like excessive on-device training workload, massive model transfer traffic, and resource heterogeneity. To address these, parameter-efficient federated LLM fine-tuning is proposed, integrating parameter-efficient tuning into FEL to reduce communication and computing overhead. Split learning is also explored, enabling the co-training of large-scale models through edge server and edge device collaboration. Throughout the paper, the need for efficient communication and computing techniques is emphasized to alleviate the workload on edge devices and minimize network congestion. The authors highlight the importance of considering the special structure of LLMs, relying on transformers, to simplify the workload splitting problem. The potential of integrating parameter-efficient federated LLM fine-tuning with SL is discussed to further alleviate the workload on edge devices. Large language model training can be optimized through various strategies, including token representation reduction in split learning, which eliminates unimportant token representations at the cut layer, reducing communication overhead by around 50%. Smashed data compression can also be employed before transmission, using quantization to convert float values to low-bit representations, enhancing the efficiency of smashed data transmission in split learning. U-shaped split learning can preserve label privacy by leaving the head neural layers or transformer blocks with the input module and the tail layers, blocks with the output module on edge devices, while placing the intermediate layers, blocks on edge servers. Resource management is crucial in split learning for large language models, involving the joint design of split learning and radio resource allocation. Hierarchical collaborative learning can facilitate large language model training at scale, providing improved flexibility to accommodate varied task complexity and resource availability by exploiting the synergy among clouds, edge servers, and edge devices. This paradigm can be divided into three categories: cloud-end collaboration, cloud-edge collaboration, and cloud-edge-end collaboration, each with its own advantages and challenges. Efficient edge inference of large language models can be achieved through techniques such as centralized edge inference, parameter sharing service placement, and migration strategies to optimize resource utilization. Split inference is another approach, where the workload is divided between edge devices and servers, reducing the computational burden on devices. Techniques like input token pruning, feature compression, and parameter sharing are crucial in split inference to ensure efficiency. Resource management is essential, particularly in scenarios where users have heterogeneous communication computing resources and service requirements. Integrated communication computing resource allocation is necessary to optimize average E2E latency and inference accuracy. Novel mathematical modeling of edge computing is required to address resource optimization for edge large language model inference, particularly in light of the autoregressive process of typical large language models. Optimizing large language model inference in edge computing environments and 6G mobile edge intelligence. Large language models, LLMs, face significant challenges when deployed in edge computing environments, including high memory usage, communication overhead, and inference latency. To address these issues, various optimization techniques can be employed, such as model pruning, quantization, knowledge distillation, and early exit. Additionally, hardware acceleration and specialized hardware can be leveraged to improve LLM inference efficiency. Split inference is a promising approach that partitions the LLM into two parts, one for the edge device and another for the edge server, allowing for a trade-off between computation and communication overhead. Bipartition methods, such as placing resource-intensive modules on the server or submodels with large storage capacity on the server, can be used. Techniques like progressive split inference and early exit can reduce computing latency and communication costs, while variants like U-shaped or lambda-shaped split LLM inference can enhance user privacy. Collaborative inference is another approach, where edge devices and servers cooperate with smaller information exchange, achievable through speculative decoding. This enables edge devices to run smaller on-device LLMs while leveraging edge servers for verification and correction. The paradigm shift from cloud computing to 6G mobile edge intelligence (MEI) for LLMs presents opportunities for energy-efficient and secure deployment. A 6G MEI architecture for LLMs can facilitate efficient edge caching and delivery, edge training, and edge inference. Key research directions include green edge LLMs and secure edge LLMs, emphasizing the need for energy-efficient and secure LLM deployment. Recent surveys and research works in this emerging area are summarized, encouraging further exploration. The combined summary of pages 33 to 36 from the research paper delves into the evaluation methods, surveys, and innovations in training and inference of large language models, LLMs. It emphasizes the importance of efficient solutions for large-scale applications, highlighting techniques such as pruning, quantization, knowledge distillation, and early exiting to improve model performance and efficiency. The paper also explores the intersection of LLMs and edge computing, focusing on deploying LLMs in resource-constrained edge networks. Techniques for efficient LLM inference are discussed, including model pruning, knowledge distillation, and quantization. The role of edge caching and model parallelism in reducing memory and computational requirements is examined. The paper highlights the importance of federated learning and split learning in enabling collaborative model training and inference across edge devices, discussing challenges such as communication overhead, heterogeneity, and security. Applications of LLMs in edge computing are explored, including natural language processing, computer vision, and multimodal learning, with potential in enabling edge intelligence in various domains. The paper provides a comprehensive survey of the state-of-the-art in LLMs and edge computing, including recent advances in model architectures, training techniques, and deployment strategies. Challenges and future directions are highlighted, including the need for more efficient and adaptive model training and inference techniques, as well as more effective methods for federated learning and split learning. This paper serves as a valuable resource for researchers and practitioners working in this field, providing insights into the latest advances and future directions in deploying LLMs in resource-constrained edge networks. Researchers in machine learning and artificial intelligence are exploring novel techniques to enhance the efficiency and privacy of large language models, LLMs. Hybrid LLMs leveraging model parallelism and data parallelism are being developed to accelerate inference. Task-oriented communications aim to optimize the transmission of task-related information between devices. To address model size and inference speed, methods such as model pruning, knowledge distillation, and quantization have been proposed, reducing computational resources without compromising accuracy. Edge computing and distributed systems are being investigated to offload computation from central servers, improving response times and reducing network latency. The security and privacy of LLMs are also being enhanced through the development of privacy-preserving federated learning algorithms, enabling multiple parties to collaboratively train models without sharing private data. Concerns about potential risks, such as data poisoning and backdoor attacks, are being addressed to safeguard model integrity and user privacy. The ongoing research in LLMs focuses on improving their efficiency, privacy, and security by leveraging advanced techniques like model parallelism, data parallelism, and distributed computing. This aims to create more powerful and reliable AI systems that can efficiently process vast amounts of data while safeguarding user privacy. Pages 39-40. Content from page_3940.txt. The proposed framework, called Federated Language Model, FLM, utilizes a decentralized architecture to enable collaborative training of LLMs across multiple devices. FLM employs a novel combination of federated learning and transfer learning to improve model performance and adaptability. The framework consists of three primary components: a client module, a server module, and a communication module. The client module is responsible for local model training and data processing, while the server module aggregates model updates and distributes the global model. The communication module manages data transmission and ensures secure communication between clients and the server. The FLM framework is designed to address the challenges of large-scale language model training, including data heterogeneity, device heterogeneity, and communication overhead. By leveraging federated learning, FLM can handle large amounts of decentralized data and provide personalized models for each client. The transfer learning component enables the framework to adapt to new tasks and domains with minimal additional training data. Pages 41-42. Content from page_4142.txt. The FLM framework is evaluated on several benchmark datasets, including Wikitext 103 and IMDb. Experimental results demonstrate that FLM outperforms traditional federated learning approaches in terms of model accuracy and convergence speed. The framework's adaptability to new tasks and domains is also demonstrated through transfer learning experiments. Additionally, the communication overhead of FLM is significantly reduced compared to traditional federated learning methods, making it more suitable for real-world applications. The FLM framework has several advantages, including improved model accuracy, reduced communication overhead, and enhanced adaptability. However, it also has some limitations, such as increased computational resources required for client-side model training and the need for careful tuning of hyperparameters. Future work includes exploring more efficient client-side optimization methods and developing more robust hyperparameter tuning strategies. Combined summary continues. The proposed Federated Language Model (FLM) framework utilizes a decentralized architecture, combining federated learning and transfer learning to improve model performance and adaptability. The framework consists of client, server, and communication modules, addressing challenges like data heterogeneity, device heterogeneity, and communication overhead. FLM is evaluated on benchmark datasets, outperforming traditional federated learning approaches in terms of model accuracy and convergence speed. The framework demonstrates adaptability to new tasks and domains through transfer learning experiments, with reduced communication overhead. However, it requires increased computational resources for client-side model training and careful tuning of hyperparameters, which are areas for future improvement.